Ladies and gentlemen, boys and girls, the time has finally arrived for us to take a more in-depth look at my favorite routing protocol of all time, which is going to be OSPF, Open Shortest Path First. It's going to be the algorithm and the routing protocol that we're going to see throughout the rest of our experiences taking exams from Cisco that they're going to use to try to trip us up and confuse us. Now, that makes it sound like it's an adversarial relationship. It's not really. But the thing is what we need to understand here is in the confines of these devices, we have tons and tons of options and capabilities. And the best way for us to be able to walk through this is going to be to entertain the idea of doing some type of overview. Now, it's been a little while since we talked about OSPF. We mentioned it loosely near the end of ICND1 conversations. And what we want to do is we want to highlight exactly what it is we're talking about and why OSPF is actually so important to us. Let's make sure that I've got everything good to go. And what I'll do is I'm going to pull my pen up and we're going to start our dialogue about OSPF. Now, first of all, OSPF is a link state routing protocol. That means it maintains a database. Now, what we need to understand about this is that this database is actually going to be maintained on an area-by-area basis. Now, our initial conversations about OSPF revolved significantly and specifically around single area OSPF. Let me go ahead. What I'm going to do is I'm going to go ahead and bounce this, and I'm going to go ahead and grab my big whiteboard. So, like I said, OSPF is a link state routing protocol, which means it maintains a database of information, and that database must be synchronized between all devices located in the same area. And like I said, we were focusing purely on OSPF in a single area environment. Now what we're going to do is we're going to kind of open the throttle in this entire process, and we're going to need to do a little bit of exploration with regard to some of the capabilities, just as a refresher. So when we look at this, what we see is like I said, we have a link state protocol, an LSP. So a link state protocol is going to give me the capability of having a more scalable topology. Now, by virtue of the fact that my topology is more scalable, I get the benefit of using this database, which I actually use as like a picture of my network. And it's a picture of my network that's going to be exchanged between all devices that participate in OSPF. The method that we're going to use to exchange this information to build this picture is going to be referred to as link state advertisements, LSAs. Now, in the confines of a single area OSPF, we had specific types of link state advertisements that we had to focus on. There were what we would reference as being type 1 LSAs, which are going to be generated by all OSPF speakers, and type 2 LSAs, which are going to be generated by DRs on an Ethernet segment or a multi-access broadcast segment. Now, these are going to be the LSAs we need to understand. They never leave an area. So if I have area 0, none of these prefixes or none of these database entries or these link state advertisements are going to be able to leave the area. If we have information that we want to exchange between areas, what we're going to do is we're going to transform and create a new type of LSA, and that LSA is going to be a type 3 LSA. Type 3 LSAs are going to be propagated by the device that sits in the middle of the two areas, provided one of those areas is either logically or physically connected to area 0. Now, the main goal here is these type 3 LSAs are called summary LSAs. And those summary LSAs take all of the type 1 information and summarize it and then broadcast it out. And the thing is type 3 LSAs by default can appear in every area that I have configured in my OSPF topology and design. Now, what we look here is this gives me the capability of being able to track the changes that may take place in my infrastructure, but by virtue of the fact that I divide my network into multiple areas, area 0, area 1, area 2, what ends up happening is an issue that takes place in area 1 is not necessarily going to affect the routing that's going to be taking place between area 2 and area 0. So again, it gives me the capability of being able to kind of scale off my infrastructure in such a fashion that we are not going to have problems cascading. So in other words, by breaking up my network into smaller areas, I define how my areas or how my routers are going to be performing and operating. And I can restrict things like issues and failures. So areas are for a lot of capabilities with regard to having this hierarchical design that Cisco's so famous for. Now, the other part of this is that when we look at this, what I want to understand is LSAs are part of my LSP, my link state protocols. Now, in the confines of a link state protocol, what do I have and how do things operate? And what is the actual nature of the data? Specifically, what I want to focus on is data structure. Data structure as it expands or as it relates to how information is going to be exchanged. One of the best ways to look at this is going to be to simply draw a network. So let me pick a smaller pin size. And what I'm going to do is I'm going to say I have 3 routers, actually 4 routers. We're going to have router A, router B, router C, and router D. Now what we're going to do here is that I'm going to have prefixes or links that I'm going to advertise. Let's pretend that these are loopback addresses. We've used loopback addresses up to this far in the discussions of every routing protocol that we're working with regard to advertising prefixes and using it for the purposes of looking at path selection, equal cost multipathing, and things along those lines. So now what's going to end up happening is this particular device, A, has this particular link that's participating in OSPF, and it's going to start advertising it. And the way that it's going to advertise it is by sending out LSAs, link state advertisements. Now these link state advertisements are going to be exchanged on each of these individual links on a hop-by-hop basis, employing the multicast address 224.0.0.5. Now we also have a 224.0.0.6 address, but we'll get into the details of that later. But what we need to understand is all OSPF speakers are going to be listening to 224.0.0.5. Now, through the exchange of this information, these LSAs, I build my database, my link state database. And from my link state database, I pick prefixes based on the shortest path algorithm that's going to be running in my infrastructure to build my routing table. So again, just like we saw in the context of EIGRP, we are going to be selective as to what information we're going to put where. Now it also means that I'm going to have some tables. I'm going to have 3 tables that I want to keep track of. I'm going to have my neighbor table. My neighbor table is going to be illustrated using the show IP OSPF neighbor command. It's going to give me a list of all of my neighbors based on our connectivity via router ID, and it's going to give me all of the associated information that I need to know. And what's going to end up happening is the links shared between these neighbors are going to be used to flood LSAs. So LSA flooding is going to take place. Now once I have that, I'm going to move to my second table. The second table is going to be my topology table. Now in the confines of my topology table, basically this is going to be in the confines of my database, and it's going to be a record of all of the information associated with my LSAs and the types of networks that they define. So for instance, I'm going to have the idea of transit networks, networks that can be used to reach other destinations. I'm going to have the idea of our stub networks. But the main thing that we need to recognize here is that this database is actually made possible through this idea of our link state database. Now, of this information, we're going to take everything that's inside this database and move to this third model, and I'll put myself over here on the other side. This third model is going to be my routing table. So the routing table is constructed by running my shortest path first algorithm against my database or my topology table and generating intricate entries that I'm going to include in my routing table for the purposes of being able to send packets to particular destinations. So that's the main nature of this. And again, it's going to be made possible through the LSAs, through the database itself, and through the shortest path first algorithm. These are the database structures or the data structures that we need to concern ourselves with. Now, the other thing that I want to make certain that we point out here is in this exact same scenario that we had before, where we have router A, we have router B, we have router C, and then we have router D, where we're also connected in kind of like a box, where we have the two networks that we want to be able to advertise. What we have to recognize now is that the metric used by OSPF has a name. We call it cost. So that metric is going to be a numeric value assigned to our link. So let's say we have 10 and 20 and we have 10 and 10. That's our metric. So for me to be able to come from here to travel to this particular prefix, what I'm going to find here is I'm going to go through here and I'm going to tally up my costs. So to get to here via this path through D, so from A to D to C is going to have a cost of 20. From A to B to C, it's going to have a cost of 30. So my cost, my lower cost is what I'm going to choose, and that's the path that I'm going to use in order to be able to reach that particular destination. Now, when we start looking at it, the idea is in the confines of metric, our cost by default is going to be calculated based on interface bandwidth. Now, when we look at that, what we need to understand is interface bandwidth in the confines of our descriptions on our switches and our routers have nothing to do with any type of real configuration. So bandwidth is not necessarily going to be indicative of the type of speed. So for instance, a serial link is going to default to 1.54 megabits. It could be 64K. It could be 128K. It could be shotgunned and operating at a higher throughput. But the main idea here is that we need to make certain that these values have direct meaning. Now what we're going to do is we're going to have a value where cost is going to equal the idea of what we call the reference bandwidth. And specifically, it's going to be the reference bandwidth divided by the actual configured interface bandwidth. Now, the thing we need to understand is the reference bandwidth is actually going to be measured in hundreds of megabits per second. So the idea here is it's going to be the calculation, and this reference bandwidth is going to directly translate to how granular my costs are going to be. Keep in mind, when OSPF first came out, it was a long, long time ago, and the fastest connection we had was 10 megabit at the time. Then we moved to 100 megabit. Then we moved to 1 gig. Now we're looking at 10 gig in our environment, or 4 gig in certain scenarios. So the thing that we need to understand is that you had to modify the operating system or the OSPF algorithm itself to take into account these faster interfaces. So by allowing us to be able to manipulate the reference bandwidth, we can control as administrators how granular the process is going to be with regard to calculating metric. Now when we look at this, it really boils down to the simple fact that until we form adjacencies, we can't really do anything. So when I set up and create an adjacency configuration, what I have to do is I have to make certain that certain values match. We already talked about in this confines of the IC and D1 connections. We need to make certain that the router IDs are unique. So they have to be different. We want to make certain that our hello and our dead intervals match on both sides of our link. We want to make certain that our area IDs match on the link. So if I have area 0 on one side and area 1 on the other, I'm not going to be able to form a relationship. We want to make certain that our router priorities are configured. We want to make certain that we have an IP address that we can use for the DR on our broadcast segments, as well as the BDR, the backup designated router. And also, if we're going to do any type of authentication, we need to make certain that the authentication matches. Now, again, these adjacencies are going to be formed by sending hello messages And those hello messages are going to be sent to the multicast address of 225.0.0.5. Now, what that directly translates to is that these are link local multicasts. So they're never going to go beyond our segment. So when I have two routers that are going to be interconnected, I'm going to send a hello just across this link. It's not going to be routed to another link. So these hellos are used to create peering relationships and create these adjacencies such that we can identify, discover, and communicate with neighbors that are on adjacent links. Now, what we have to understand here is the values that absolutely positively must agree on include the hello and the dead interval, the area ID, and the authentication configuration. Another value here that's going to be really important is we also need to be able to agree on something called the stub flag. Now, we may not get into that portion of the conversation, but the stub flag allows me, we talked about stubs in passing, it allows me to say that this network, so R4 in this scenario, goes nowhere. So I'm not transit for anything. So what I can do is I can say I'm a stub and I can use a default prefix or a static default route to come out of that infrastructure without having to run the actual interior routing protocol and keep a record of all of the information in it. Now, what we want to understand is that when we go through here and we look at how we build our database, the database is all-encompassing. It's the most important element that we can deal with in the context of OSPF. The database lists a record of every one of our individual LSAs, the information that's being advertised by each, and it gives us a holistic approach with which we can create our routing table. The routing table is how we actually do forwarding of information. So forwarding. Now, looking at this, what we need to recognize here is we have two devices that are interconnected. Let's just say they're routers, and we have a network out here, and that network is going to be, say, 10.1.1.0/24. Now, when we look at this, what's going to end up happening is at some point during our adjacency process, we're going to enter a procedure that's going to be referred to as exchange start. It'll actually be designated as XSTART, EXTART. Now, what this is telling me is that my adjacency is up, and now what I want to do is I want to get ready to start sending information between these routers, R1 and R2. So what's going to end up happening is that rather than send all of my prefixes via broadcast like we would if we were working with RIP, what I'm going to do is I want to first exchange information so that I can make this process very, very controlled and very constrained. So what we're going to do is the moment we hit exchange start, we're going to start exchanging information about prefixes, but we're not actually exchanging the prefixes themselves. What we're going to do is we're going to be sending messages that are going to be involving something called DBDs. That stands for a database descriptor. It's a packet that we're going to be sending. And what it's going to do is that we're going to exchange this between both of these devices, DBDs. This is going to be our link state database summaries. DBDs, database descriptors, is just a list of everything that I know, and I'm going to exchange it. And then it's going to arrive at the other device. That device is going to look at it and say, okay, I know about this one, I know about that one, I know about this one, I don't know about this prefix, I don't know about that one, I do this one, this one. So there's 3 prefixes I don't know anything about. So what it's going to do is it's going to notify the other device that I don't know about 3 of these, send me the information in the form of updates. Actual updates. So when I send it, what's going to end up happening, the system is going to come back and it's pretty much going to say, hey, thanks, dude. I've got the list. So now when we start looking at this, what's going to happen is that the next step in here is going to be the fact that we want to make certain that this thanks is registered. And it's going to be registered through something called a link state acknowledgement, an LSACK. Now, once we have this acknowledgement, now what I'm going to do is I'm going to say, well, I need information. So what I'm going to do is I'm actually going to say, I need information for the entry of 10.1.1.0 here. And that's going to get sent out to the system. So I'm trying to say, I don't have this prefix, you do, send me the information about it. Now, the moment that I do this, I've actually sent a new type of message. It's referred to as a link state update. Now, the moment it's received on the other end, keep in mind the system is going to send me that data. It's going to say, okay, here is all the information I have on 10.1.1.0 /24 here. Then basically what's going to end up happening is that's going to come to me also in the form of a link state update. Then what I'm going to do basically here is just simply acknowledge the fact that I received it, again with an LSA CK, an actual acknowledgement. So what we can see here is we have a very organized structure with regard to how we exchange information between our individual devices on a link-by-link basis. And also keep in mind, we also have in the confines of OSPF this idea of our structured approach, hierarchical design, HIERARCHICAL. You know what? They should actually make this a requirement to know how to spell this to pass the CCIE. Because when you're looking at doing these deployments, hierarchical design is going to be Cisco's go-to approach, because hierarchical implies order. Order implies method. Method implies operations. So what we end up having here is that we have a hierarchical infrastructure because we're using areas. And what we need to recognize is that areas have to have structure. They have to have order. They have to have some kind of governances over top of them. So if I were to have a series of routers here where I have R1, I have R2, I have R3, and each of these devices are connected in two different areas. Let's say area 0 here. Let's say over here I've got another router, R5, and it's going to be area 1. Over here I'll have a second area. Actually, I'll pick another color here. I'll pick purple. And I'm going to have area 2. Lastly, we'll just draw another here. I'll just take a dashed line here, and I'll pretend I have another router in my infrastructure here that say it's R4. And what I'll do is I'll use a dashed line to represent this area, and we'll say this area is going to be an external autonomous system, an external AS. Now, when I start looking at this, irregardless of connectivity in these individual clouds, what I have to recognize here is I have area 0. And what I need to know here is the area 0 is going to be referred to as our backbone area. Now, this is going to imply that traffic is going to have to traverse it. The traffic I'm talking about is control traffic. Control traffic has to traverse the backbone area. So in order for me to make certain that I have intercommunication in a multi-area OSPF deployment, what I have to do is I have to ensure that I am either physically adjacent or logically adjacent to area 0 in every one of my VLANs, or I'm sorry, in every one of my areas. Now, what we have here is the backbone area, and these other areas are referred to more commonly as normal areas, except for the external area. So that's our two levels. We have the backbone and we have our normal areas. Again, it's hierarchical, and it also allows us to be able to confine what's happening. Now, when we start looking at this, it's important for us to understand that our system is going to have role-based behaviors. Now, again, Cisco's really big about role-based behaviors. And what we need to look at is the fact that we have different roles that we can assume. So the first role that I want to point out here is I'm going to have a backbone router. The next one is going to be an internal router. I'm going to have autonomous boundary routers, and then I'm going to have autonomous area border routers and autonomous system boundary routers. Now, a router that is going to take information from an external autonomous system and send it into into OSPF is the veritable definition of an ASBR, an autonomous system boundary router. And really and truly, what it's going to typically be doing is redistribution. So that takes ASBR off the list. An ABR is an area boundary router. An area boundary router is going to be any any device that has interfaces that exist in multiple autonomous systems, or multiple areas, excuse me, provided that one of those areas is area 0, either logically or physically. The other thing that we see here is a backbone router is going to be any router that's going to allow us to traverse across area 0. That means an internal router is going to be any area that only has interfaces in a single autonomous or in a single area. So recognizing exactly what's happening here becomes really important, because what happens is that our LSAs are going to be advertised based on these role assignments. So let's take a look at that. So first and foremost, let's operate under the assumption. I'm going to go ahead and grab the thinnest pen that I have. Let's operate under the assertion that we have router 3 here, R3. Now R3 is connected to R2, and also we have R1 in this topology. Now what we need to recognize is first we have areas. So what I'm going to do is I'm going to define an area here. We're going to call this area 1. Next, what I'm going to do is I'm going to grab area 2, and I'm going to make certain that it's configured. So now I have area 2. Now, what we have to also recognize here is that I have the capability of having another autonomous system. This is going to be that idea of an external AS. So an external autonomous system. Now, in the confines of this particular style of configuration, what we need to recognize now is what is going to be advertised based on this concept of LSAs, link state advertisements. So looking at this, what we see here is that we are connecting to these devices, and these devices are going to be sending LSAs. So for instance, in the confines of R3 and R4, we're going to be sending type 1s or type 2s or both between these devices. These type 1s or type 2s are never going to traverse this boundary. So again, here I'm going to have the same concept. I'm going to be sending type 1s or type 2s or both between devices in the other areas. And all of those type 1s and type 2s are going to be contained in our given areas. Now the other part of this is that here is the issue. If I want to be able to have communication take place such that R2 or such that devices inside of area 1 can reach area 2, I need another kind of LSA. I need an LSA that's going to take these type 1s and type 2s, and it's going to actually generate a new LSA that can be used to traverse across the boundaries between areas. That is going to be what we refer to as our type 3 LSA. So what's happened is that a type 1 and 2 LSA is going to be generated by an actual router. Type 1s are generated by all routers. Type 2s are only generated by DRs, designated routers. Type 3s are going to be generated only by ABRs, area boundary routers. Now what we're going to see here is the fact that these type 3 LSAs give me reachability information for prefixes that exist in this infrastructure. But the problem is this type 3 LSA is never going to be created in the scenario that we have right here, because we do not have an area 0. Area 0 is a requirement for Cisco to recognize a device as being an actual ABR. So if I were to create a loopback interface here and place it in area 0, now what ends up happening is I can actually generate these type 3 LSAs. I simply just want to make certain that that's driven home. Now, when we start looking at this, it's also going to be important for us to realize that in this scenario, R3 is going to be working as an ASBR, an Autonomous System Boundary Router, which means it's going to begin originating a new type of LSA. It's going to illustrate or do what's called a type 5 LSA. Now, type 5 LSAs can go between areas, and by default, we're going to find that they're going to actually be present in all areas. Now, the instance here is that what we need to understand is R3 has a type 1 LSA associated with it. So if I come up here and I say, okay, I'm an actual autonomous system boundary router, here's my address, and this is going to be what you use to reach this external system, what happens here is that the information that is being communicated does not give this area, area 2, the ability to be able to reach over here because it's simply not advertising a prefix. So what we're going to do is we're going to create a new type of LSA, an LSA that's referred to as a type 4. LSA type 4s are generated by my ABR. So all it's going to simply do is it's going to take the type 1 LSA for the ASBR, and it's going to copy it, and it's going to create a type 4 LSA so that now not only do I get the identity of the ASBR, I now know, because of the type 4, how to reach the ASBR. So it's the reachability information for the ASBR that we have in our configuration. And keep in mind, like I said, type 5 LSAs go everywhere inside of our infrastructure. So we've described 4 LSA types. Type 1, actually we've described 5, is going to be a router LSA. Router LSAs are type 1s. Type 2 LSA is going to be a network LSA. Only generated by an ABR, only generated by a DR on a segment. We have a type 3 LSA, which is referred to as a network summary LSA or just straight summary LSA. Again, generated by an ABR. We have a type 4 LSA. A type 4 LSA is referred to as an ASBR summary. The ASBR summary is also generated by an area border router, an ABR. Then we have the type 5 LSA. The type 5 LSA is generated specifically by an ASBR, and it's referred to as the Autonomous System LSA, and it's going to be, like I said, populated to all areas in my infrastructure to include Area 0. So seeing how this all goes into play, we can see exactly what's happening when we start bringing all of these devices up. And these control plane mechanisms are exceedingly important to the normal and practical application of OSPF. Now what I want to do is I want to take the opportunity to continue working with this, and hopefully we're going to reach a point to where I can feasibly do a demonstration using regular OSPF. So let's take a look at that in the next lesson. I'll see you there.